We now start chapter 8 module 1 and we will be talking on modules. We have learned definitions of vector spaces, which are linear structures where the scalars come from a field. We can generalize that structure where the scalars come from a ring. We call such structures module structures on a set. In some sense, they are generalizations of the vector space structure. We will assume that the rings are commutative with identity, and we first learn the basic properties, and then we will see that the main difference between a module and a vector space should be that a module may not have a basis. So, let us first start with definitions and basic properties. Let R be a commutative ring with identity. A non-empty set M is called an R module or a module over R if there exists a binary operation plus on M and a map or scalar multiplication mu from R cross M to M, which we denote by mu of R comma V is equal to R dot V, such that the following properties are satisfied. 1. M with respect to plus is an abelian group. 2. For every CD in R and UV in M, C dot U plus V is equal to C dot U plus C dot V. C plus D dot U is C dot U plus D dot U. CD dot U is C dot DU, and 1 dot U is equal to U. And the ring R is called the base ring of the module M. Example, take the Cartesian product of the ring R n times, that is R raised to n. This is a module over R with respect to the following pointwise operations given by the n tuple a1 a2 an plus n tuple b1 b2 bn is the n tuple a1 plus b1 comma a2 plus b2 etc. up to n plus bn, and C dot a1 a2 an is ca1 comma etc. can, and this is true for every a1 a2 an b1 b2 bn in Rn and C in R. Another example, the set M and R, that is the collection of all M cross n matrices over the ring R, is a module with respect to the usual matrix addition and scalar multiplication. Another example, a non-empty subset I of the ring R is called an ideal if I is a subgroup with respect to addition and Ci is contained in I for every C in R. That means, if I take any element x from I and take Cx, then that belongs to I, and this must be true for every C in R. Then every ideal in R is naturally a module over R, and in particular R being an ideal itself is a module over R. Another example, let V be a vector space over a field F and T from V to V a linear operator. We can define a module structure on V over the ring Fx in the following way. So, Fx is the polynomial ring over the field F, and the module structure is given through this scalar multiplication. So, take any polynomial Px in Fx given by a0 plus a1x and so on up to an x to the power n. If V is a vector in the vector space V, then we define Px dot V is equal to Pt of V, where Pt is the operator a0i plus a1t and so on up to an t to the power n, and therefore Pt of V means this operator being applied to V, which would produce another vector in V. This is an extremely important module structure on a vector space with the help of a linear operator. A definition: let M be an R module, a non-empty subset N is said to be a submodule of M if N is an R module with respect to the restriction of the addition and scalar multiplication on the set N. In other words, the theorem says that let M be an R module, a non-empty subset N is a submodule of M if and only if for every uv in N and cd in R, the element cu plus dv is an element in N. This follows from the definition of submodules. Let us now define the sum of submodules, and the definition is almost the same as that for sum of subspaces for a vector space. Let n1 and n2 be submodules of a module M over R. The sum n1 plus n2 is defined as the set of all elements of the form v1 plus v2, where v1 belongs to n1 and v2 belongs to n2. And in general, if ni, I running over an index set lambda, is a collection of submodules of M, then the sum is defined as summation ni, I belonging to lambda, is the set containing elements of the form v1 plus etc. up to vk, where vi belongs to the union of all the ni's I belonging to lambda, and k runs through the set of natural numbers. It is easy to prove that this summation ni, which is the sum of the submodules ni's, is the smallest submodule containing ni for every I in lambda. And a very important property is given in this theorem, which says that if n1 and n2 are submodules of a module M over R, then the intersection of n1 and n2 and the sum n1 plus n2 are submodules of M. These are all easy verifications with the help of the definitions. Definition: let M1, M2 and so on Mn be modules over R, then the external direct sum of M1, M2 and so on Mn is denoted by this M1 box plus M2 box plus and so on box plus Mn, where the underlying set is nothing but the Cartesian product of these modules, that is M1 cross M2 and so on Mn, that is the set of all n tuples of the form v1, v2 and so on vn, where vi's are in mi's, and the module structure is with respect to the pointwise addition and scalar multiplication defined as an n tuple v1, v2, vn and an n tuple w1, w2, wn. The addition is defined as v1 plus w1 and so on vn plus wn, and c dot v1, v2, vn is cv1 comma etc. up to cvn, and this is for every n tuples v1, v2, vn, w1, w2, wn in M and c in the base ring R. Another definition: a module M over R is called an internal direct sum of the submodules n1, n2 and so on nk of M, denoted by M is equal to n1 direct sum n2 and so on nn, usually we denote this symbol by O plus. If the following properties are satisfied: 1. M is equal to N1 plus N2 dot 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 plus Nk, and 2. Ni intersection summation Nj j not equal to I is the singleton, the 0 element of M, where this 0 is nothing but the additive identity of M plus. In other words, every element V in M can be expressed as V is equal to V1 plus dot 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 Vk for unique choice of elements V1 in N1, V2 in N2 and so on Vk in Nk. Example, the module Rn is the external direct sum of the modules R, n many, over the base ring R. On the other hand, it is the internal direct sum of the submodules Ni, where Ni is given by this singleton 0 times so on singleton 0 times R times singleton 0 times so on singleton 0, where R is sitting at the ith position and all other positions are filled with the set singleton, the 0 element of the ring R. We have learned definition of modules, submodules, sum of submodules, and also the internal and external direct sums. We have seen that there is hardly any difference from the vector space situation. These concepts were introduced for vector spaces, and it is almost the same for modules. We will see a difference when the base ring comes into the picture, in the sense that when we have to use invertibility of scalars, the difference we have is in the base ring, which may not be a field, and therefore there will be elements which are not invertible. Now first we introduce the notion of spanning sets. This will also be similar to that in vector spaces, and then gradually proceed towards the notion of linear independence, free modules, etc. Let us see. Definition. Let S be a subset of a module M over R. The span of the set S, denoted by span S, is the set of all these linear combinations C1 V1 plus dot 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 plus Cn Vn, where Ci's are coming from the base ring and Vi's are in the set S, and N is running through the set of natural numbers. A subset S is said to span N or generate N if N is equal to span of S. The element written as C1 V1 plus dot 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 plus Cn Vn, such that Ci belongs to the base ring R and Vi belonging to M, is called a linear combination of the elements V1, V2 and so on Vn. And if S happens to be the empty set, then we write span of S is equal to singleton 0, where 0 is the additive identity of the module M. We will use the symbol 0, which is not in boldface, to denote the additive identity of the base ring R, whereas the boldface 0 stands for the additive identity of the module M, just like the notations we have used for vector spaces as well. Now, a simple theorem which says that if S is a subset of a module M over R, then span S is the smallest submodule of M which contains the set S. This is easy to verify. Definition: a submodule n of a module M over R is said to be cyclic if n is the span of a singleton set, that is singleton V, for some V in n, and n is said to be finitely generated if n is equal to span S for some finite subset S of n. Let us look at this example. R denotes the polynomial ring over the field F in infinitely many variables x1, x2 and so on, xn and so on. Let n denote the span of the set S, which is the set of all the variables. Then n is not a finitely generated submodule of R over the ring R. Why not? Suppose that n is generated by finitely many polynomials, say f1, f2 and so on fk. Now each polynomial involves at most finitely many variables by definition of the polynomial ring. Therefore, finitely many polynomials f1, f2 and so on fk can involve at most finitely many variables from this infinite set of variables. So, suppose xr is a variable which is not appearing in any one of the fi's, then it is an easy observation that xk cannot be expressed as a linear combination of f1, f2 and so on fk over R. And that proves that the span of S cannot be finitely generated as a submodule of the module R over the ring R. Definition: let n be a submodule of a module M over R. A coset of n in M is a set of the form V plus n, which denotes the collection of all elements of the form V plus W, where W belongs to n, and for some V in M. Example: suppose that M is R2, that is the Cartesian product of R with itself, and W is the set of all ordered pairs x comma 0 such that x belongs to R. If V is an element a comma b, then the coset V plus W is nothing but the set of all ordered pairs of the form x plus a comma b, where x is running through the ring R. A proposition: let n be a submodule of a module M over R. Let V1 plus n and V2 plus n be two cosets of n in M. Then exactly one of the following holds, that is V1 plus n intersection V2 plus n is the empty set, or V1 plus n is equal to V2 plus n. Moreover, V1 plus n is equal to V2 plus n if and only if V1 minus V2 belongs to n. You can see that this is exactly the same as that for vector spaces, and it is an easy verification which follows from the definition. We can define an equivalence relation on M in the following way, just like we did for vector spaces. So, let n be a submodule of a module M over R. Given elements V1 and V2 in M, we say that V1 is related to V2, written as V1 tilde V2, if and only if V1 minus V2 belongs to the submodule N. In the language of cosets, V1 tilde V2 if and only if V1 plus N is equal to V2 plus N, and it is an easy verification that tilde is an equivalence relation on the module M. And given V in M, the coset V plus N is the equivalence class of V, and we often use V bar to denote the equivalence class, which is nothing but the coset V plus n, and the collection of all equivalence classes or cosets is what is called the quotient set, denoted by M quotient n or M modulo n, and the elements of the quotient set are therefore equivalence classes or cosets, and we can define addition and scalar multiplication on M modulo n in the following fashion, that for every V1 V2 in M and C in R, we define V1 bar plus V2 bar is equal to V1 plus V2 bar, and C dot V1 bar is equal to C dot V1 bar. Let n be a submodule of a module M over R, then the following operations are well defined. These are precisely the operations that we defined just now on the quotient. So, V1 bar plus V2 bar is V1 plus V2 bar, where V1 V2 are in M, and C dot V1 bar is equal to C dot V1 bar, where V1 is in M and C is in R. And how do we check the well definedness? We assume that V1 bar is the same as V1 dash bar and V2 bar is the same as V2 dash bar, and prove that V1 plus V2 bar is the same as V1 dash plus V2 dash bar, and C dot V1 bar is equal to C dot V1 dash bar. These are easy verifications, and what is to be understood here is that the equivalence class of V1, that is V1 bar, may be represented by another element V1 dash, and we have to check that the definition of addition and the scalar multiplication, they do not depend on the representatives. Now we define a homomorphism between modules. Let M and M dash be modules over R. A map F from M to M dash is called a homomorphism over R if F of C dot U plus D dot V, C dot FU plus D dot FV for all C and D in R, and UV in M. And a bijective homomorphism is called an isomorphism. And if we collect all the homomorphisms from M to M dash over R and denote it by hom M M dash R, then this set has a natural R module structure under pointwise addition and scalar multiplication given by F plus G of V is FB plus GV, and C dot F of V is equal to C dot FV, where C is in the base ring R, V is in M, and F and G are homomorphisms from M to M dash. Given homomorphism F from M to M dash, we can define the sets kernel and image in the usual way, that is kernel of F is equal to set of all those elements V such that FV is equal to 0. That 0 in boldface is the additive identity of the module M dash, and ImF is the image F, which is the collection of all elements of the form FV where V belongs to M. Both CarF and ImF are submodules of M and M dash respectively. And now let us list down a few theorems which help us understand the submodules of the quotient module. To begin with, the correspondence theorem, similar to that for quotient vector spaces. This says that let n be a submodule of a module M over R. Let S denote the set of all submodules of M such that n is contained in T is contained in M. Then the map eta from S to M mod n given by eta of T is equal to T mod n is an order preserving 1-1 correspondence. This is an easy verification, and it says that the submodules of the quotient module M mod n is of the form T mod n, where T is a submodule of M which contains n. The usual isomorphism theorems like quotient vector spaces. So, the first isomorphism theorem says the following: let M and M dash be modules over R, let F from M to M dash be a linear transformation over R. There is a well defined 1-1 linear transformation F dash from the quotient module M quotient kernel of F to M dash defined as F dash of V bar is equal to F V bar. Moreover, F dash is an isomorphism if F is onto. The second isomorphism theorem says, let M be a module over R, let N1 and N2 be submodules of M, then the quotient module N1 plus N2 mod N2 is isomorphic to the quotient module N1 mod N1 intersection N2. You can see that N1 plus N2 is a submodule of M which contains N2, and therefore N1 plus N2 modulo N2 makes sense as a quotient module, and similarly the submodule N1 contains the submodule N1 intersection N2. So, once again the quotient structure makes sense. And the third isomorphism theorem, which says that if M is an R module and N1 contained in N2 are submodules of M, then the quotient module M mod N1 modulo N2 mod N1 is isomorphic to M mod N2. Here also M mod N1 makes sense because N1 is a submodule of M, and again N2 mod N1 makes sense because N1 is contained in N2 as a submodule, and then we have this isomorphism. Whatever we have learnt in this module are more or less the replica of those which we did for vector spaces. The concepts of direct sums, quotient, and of course sum of submodules, etc. But now we proceed towards the concept of freeness, which is automatic for a vector space but which is not for the case of a module. So, what we will see in the next module is that a module is not necessarily free. In other words, it may happen that a module does not have a basis.